In this problem, we have an opportunity to look at the relationship between pressure and volumetric strain. We imagine a cube being pressurized at a high pressure of 102 atmospheres and trying to understand how do the lengths of the sides of this cube change under this high pressure. Let's go ahead and get started by writing out the relationship between pressure and volumetric strain. They are related through the bulk modulus, which is what we call K. So we have pressure, bulk modulus, and volumetric strain. And the volumetric strain is just the change in volume of this cube divided by its initial volume. And if you look at the previous slides or the lecture that we had, you'll see that for this cube, it's about equal, the volumetric strain that is about equal to epsilon x plus epsilon y plus epsilon z. And in a cube, we also know that the change in length divided by the original length for each one of the sides is going to be the same. And so epsilon x is equal to epsilon y is equal to epsilon z. And we can say that the volumetric strain is going to be approximately 3 times this linear strain in any one of these directions. Now we can substitute this expression for the volumetric strain into our original Hookean relationship that we have there. And we can write out with some rearrangement that the linear strain is going to be approximately equal to minus p over 3k. What is the definition of linear strain? Well, it's just the change in length over L naught. We kind of said that a few seconds ago. And so we can go ahead and relate these expressions to each other through epsilon x, and we get that the change in length is going to be approximately equal to minus p times L naught, the original length of, well, all the sides, divided by 3k. Now, what is this k? Well, that's the bulk modulus, and the bulk modulus for a linear isotropic elastic material can be given by this equation. And again, if you want, you can go back and look at the derivation of this formula. So for polycarbonate, we've stated in a couple slides back, actually, in the lecture, that we have 2.2 gigapascals for its elastic modulus and a Poisson's ratio of 0.36. This means that the bulk modulus comes out to be 66.7 gigapascals. So now what we need to do is essentially plug in this bulk modulus, plug in the appropriate values here, and see what the change in length might be. So to do this, we'll go ahead and okay, let's do it in Python. We'll skip the Google this time. So we'll open up a notebook and go ahead and import numpy as MP, control enter, and we'll put in there some more thinking. Well, that's okay, that's fine. What do we have for values or variables? We have that expression, so we have a pressure, which is going to be equal to 102 atmospheres. Now, what are atmospheres? That's going to be equal to 101.3 kilopascals. So E3, and then we have units of pressure, like that, pascals. We have L naught, which is going to be 0.9 meters. So we'll just leave it like that. We have K, which is going to be, I guess we'll just go ahead and skip the calculation. We'll trust that we did it before, but if we wanted, we could do K is equal to E over this 3 times quantity 1 minus 2 nu, and we'll just go ahead and calculate this out. So we have that epsilon x is going to be equal to minus P times L naught divided by 3 times K. And we're going to print x like this, and we have MP.round. Okay. Oh, I didn't. I thought I had kept it for me. Sure, we can do a couple. Now it's saying it wants it in millimeters. Okay, so let me just write down millimeters here, but we should go back. Um, and no, it's not epsilon x. That's what happens when you don't see things. It's delta L. Okay, so let's just change that. Sorry about that. Some of you might have been screaming, no, you're putting it in wrong. Delta L. Okay, and it's going to be in millimeters, so we got to multiply by 1,000, just like that. Okay, and let's see what we get. We get L naught is not defined. Okay, sure, that's because that's wrong. Okay, and we get minus 0.05 millimeters. If we want a little bit more resolution in that answer, we can go to 3 decimal places, so we get about 46 microns as the result. Okay, I hope you found this video useful for calculating out the change in length of a cube under pressure.